Objects in the Kuiper Belt. It takes Sedna 11,000 years to orbit the Sun. With an orbit that elliptical, Sedna travels much faster when it's close to the Sun, the area highlighted in pink, and spends much more time at the far end of its orbit. How much more time? Well, we've sped up time here a lot. The numbers down front are years going by. Look at the orbits of the planets. The planets are moving so fast they're just blurs, even Neptune, and it takes 165 years to orbit the Sun. Now look at Sedna, far in the distance, barely creeping along as the centuries roll by. When Mike and his team discovered Sedna with the 48-inch telescope at Palomar, it was in the part of its orbit closest to the Sun. Now, it only spends about 200 years out of its 11,000-year orbit close enough and therefore bright enough to be seen with a telescope that size. So think about that. Out of the 110 centuries it takes Sedna to orbit, Mike and his team found it during the 2 when it was close enough to see. Now, it could be they just got lucky. But what if there were lots of Sedna-like objects? In any given century, there would be a handful close enough to be detected with that telescope. It turns out there are several objects with orbits like Sedna's, and it's these objects that are giving us evidence there might be a true 9th planet out there. You can see the evidence if, instead of looking at all the objects in the Kuiper Belt, you narrow it down and look just at the ones that go the farthest, so they're least affected by the 8 planets. You notice anything curious about these objects? See how their orbits are all extended on one side of the solar system? It's not exact, but they're all definitely on the right and not the left. Turns out there's only about a 1 in 10,000 chance the orbits would be aligned like that. And even stranger, these orbits should all precess like this. They should spin around the Sun at different rates. So even if they started off aligned, they wouldn't stay that way over a few 100 million years. Unless something keeps them aligned. Something massive and very far from the Sun. We call that something Planet 9. This computer simulation shows how Planet 9 would affect the orbits of distant Kuiper Belt objects. The 4 small circles are the orbits of the gas giant planets, and the large circle is Planet 9's. We're starting this simulation in the very early days of the solar system, so these additional orbits are a random distribution of early Kuiper Belt objects. Over the next minute, we'll see 4 billion years go by. The gravity of Planet 9 tugs on the Kuiper Belt objects, changing their orbits and even ejecting some of them out of the solar system altogether. It was simulations like this one that Mike Brown and Konstantin Batygin used to predict the existence of Planet 9. Brown and Batygin ran many computer simulations to figure out what mass and orbit Planet 9 would need to explain the orbits of objects like Sedna that we've observed. Well, eventually things get pretty cleared out. We see a lot of orbits precessing in the Kuiper Belt closer to the Sun, and then a number of objects with orbits extended off to the right, just like what's been observed in the actual Kuiper Belt. Planet 9's gravity acts kind of like a sheepdog with a herd of sheep. It keeps these objects from straying too far from one another. So Planet 9's orbit is on the left, and these objects like Sedna are on the right. So where is Planet 9? Well, the simulations don't tell us exactly. They give us a range of possibilities of where to find it. Each of these orbits is a possibility. Any of these orbits could explain what we see. And when viewed from Earth's perspective, these orbits cover a large swath of the sky. And as Earth orbits the Sun, we can only see some of these areas at certain times of the year. It's like finding a needle in a haystack. Or maybe not quite that difficult. The simulations at least tell us which part of the haystack to look at. But it's still a lot of work to find it. There's a lot of sky that needs to be searched. This is why finding undiscovered objects in our solar system is not an easy task. Since Planet 9 is so far away, it will be extremely faint and require a very large telescope to find, much larger than the 48-inch telescope at Palomar. That's why Mike has come here to the big island of Hawaii, almost 14,000 feet above sea level, on the summit of Mauna Kea, to begin his search with the Subaru telescope. This telescope is operated by the National Astronomical Observatory of Japan, and it's equipped with the Hyper Supreme Cam, a giant camera capable of imaging very large areas of the sky. This camera has 870 megapixels. A good smartphone has about 10. And it's attached to a telescope over 25 feet across. This camera makes Subaru the best telescope in the world for finding Planet 9. We're watching the first night of Mike's official search for Planet 9. The telescope is scanning the sky, looking in areas where the computer simulations say this elusive planet might be hiding. It will image each area 3 times during the night. And if we get lucky, in one of those areas there will be something moving very slowly. Fortunately, the weather cooperated, and conditions were pristine for the first night of the search. Many other astronomers are joining the quest for Planet 9, not only here on Mauna Kea, but utilizing telescopes around the world, even spacecraft throughout the solar system. Hopefully soon one of them will observe Planet 9. It might not happen tonight. It might not even happen this decade. But when it does, our solar system will suddenly get much, much bigger.